All right, this is the last section in the energy unit, or at least our intro energy unit, I should say. So section 5.5 is all about power. This is another word that is misused quite regularly in your day-to-day life. But power is the rate at which we consume energy. So it's the change in energy over change in time. So if you were to think about it like we did in kinematics, where velocity is the change in distance over time, power is the change in energy over time. Okay, so it's going to have units that are joules per second. Okay, but instead of calling them joules per second, they call them watts. Okay, so if you want to look here, there's a joules per second. It's the same as a watt. Okay, so add this little red box to your formula sheet. It's one of our new formulas. Oops, highlighting things where I don't want to. Let's get that pen tool going. Thank you. Okay, so power equals the change in energy over the change in time. Or you could say that the net work done over the change in time. Okay, so how much power does a swimmer produce if she transforms 2.4 kilojoules of chemical energy in food into kinetic energy and thermal energy in 12.5 seconds? Okay, well, power is equal to energy over time. So power here, we have 2,400 joules. Notice I wanted to go out, change that prefix from kilo and get it out of there because watts is measured in joules per second. Okay, over 12.5 seconds. And if we divide those two, so we have 2,400 divided by 12.5, I get 192 joules per second or watts. So once again, we've got a nice small little formula. So the math side of this shouldn't be an issue, but just keeping track of where things go and watching the units, that'll be something we'll have to watch for. Okay, a 64 kilogram student climbs from the ground floor to the second floor of his school in 5.5 seconds. The second floor is 3.7 meters above the ground floor. What is the student's power? Okay, so if we look at the work done, we could look at the change in energy. So we could look at that student's change in energy or potential energy, or we could do this with work equals force over displacement. We got a whole bunch of different ways we can look at this. I'm just going to do it with a potential energy change. So we have 64 kilograms times 9.8 times 3.7. So that's the change in energy. Okay, so 64 times 9.8 times 3.7. So we have 2,321 joules. You might also notice that these guys right here, that's a force. Force times a displacement, that's the same as a work expression. Okay, and now we want to get that. That's our energy, right? And we can do this in 5.5 seconds. So our power is going to be our energy over time. So 2,321 joules divided by 5.5 seconds, and we can figure out how powerful this student is. If you want to try a little fun experiment at home, you can take your mass, time yourself, and run up your stairs. Okay, and you can figure out how powerful you are. This is 422 watts. So that's how fast they're burning energy in that 5.5 seconds. Okay, so electrical power. If you take your power expression and you rearrange it to isolate the energy, so power equals E over T. So if you multiply both sides by T, you get energy by itself. Okay, and this is a really important concept, especially with some of the electrical appliances around your house. Okay, so what is the power of an electric elevator motor if it uses 2.9 times 10 to the 5th joules of electrical energy to lift an elevator car 12 meters in 16 seconds? Okay, so we're looking for power here, energy over time. The 12 meters means nothing in this question. We don't actually need it. So we're asked for power. We have 2.9 times 10 to the 5th joules, and we're going to consume that in 16 seconds. So if we punch that in, 2.9 times 10 to the 5th divided by 16, I get 18,125 watts, which might also be written as 18.1 kilowatts. Okay, so energy ratings and the cost of electricity. This is a really strange term, and we'll talk about where it comes from, but this kilowatt hours is a measurement of energy. Okay, so what you need to look at is this is a power kilowatt. Watt is a measure of power, and hours is a measurement of time. So when you multiply those two things together, you actually get an energy. So kilowatt hours is a unit of energy. Please star that. That's really important to know. I have a little sample table over here of what some of the appliances in your house consume. Of course, it's not fixed, but just if you went and you looked at their little electrical label, you could see what the wattage is on them. So a microwave oven, 600 to 1500 watts. It doesn't run for a long period of time, so it doesn't consume or cost you that much to do that. But if you look at your refrigerator, it runs all day. Your stove is a very large consumer of electrical energy. So if you're looking at your electrical bill, which you can maybe ask your parents or your guardians to see, and you can see time of use and a whole bunch of interesting things, it's a very valuable experience. If you are in the process of buying appliances, or if you've walked through an appliance section in a store, your parents have bought them, whatever, you might see a sign like this. Okay, where it says 900 kilowatt hours per year. That's an average. Okay, but they put 900 kilowatt hours on there as a guide. Okay, and they use this kilowatt hours because if they were to put this in terms of joules, people would freak out. The number of joules, the magnitude of this number in joules, as I'll show you in a second, is so large that it doesn't matter what your background is, you would be turned off by a number of that magnitude. Okay, and it would be hard to see how efficient the actual item is. So I have an example here, 900 kilowatt hours. I'm going to turn it into joules. I'm going to use all of the strategies we've used in previous conversions. Okay, so I have 900 kilowatt hours. So I'm going to change to yellow here. So a kilowatt is the same as 1,000 joules a second. Okay, and an hour, I'm going to turn that into 3,600 seconds. Okay, so now if I multiply those together, let's get rid of that screen if I can. There we are. Then I have 900 times 1,000 times 3,600. This is how many joules in a year that appliance would use. Okay, so 3,240,000,000 joules. Now I don't care who you are, that's going to freak you out. You're going to think that's a really big number and a lot of energy. So we use something else called a kilowatt hour. Even if you trim this down using prefixes, you still get 3,240 megajoules, which still sounds huge. Okay, but what I want to point out right here is this. So if we just looked at the kilowatt hour piece right here, this in the green box is 1 kilowatt hour. Okay, so if you multiply 1,000 joules per second times 3,600 seconds, those seconds would cancel and you would get this. So 1 kilowatt hour is equal to 3.6 million joules. Please star that, put that on your formula sheet. It's kind of a handy thing to have. And I'm going to show you two ways to work with problems on this. There's a fast way and then there's a painful way. But you should know both because you just should. Okay, what is the cost of operating a 25 watt light bulb 4 hours a day for 6 days? Okay, and we'll get to the price in a minute, but we're going to find how much energy this uses in the first place. So 25 watts is 25 joules per second. So that's where I'm going to start with this problem. 4 hours a day. Okay, so I'm going to need a conversion here. So I'm going to have, there are 3,600 seconds in 1 hour. This is going to run for 4 hours every 1 day, and I'm going to run this for 6 days. Okay, so if we do a quick little check here, the days are going to cancel, the hours are going to cancel, the seconds are going to cancel, and whatever I get here as my multiple, I should end up with something in joules, which is an amount of energy. Okay, so if we go 25 times 3,600 times 4 times 6, I get 216 and 4 zeros. So what's that? That is 2,160,000 joules. Okay, if I take this conversion up here that I've placed on here and I set up a little conversion and I say 3,600,000 joules is the same as 1 kilowatt hour, then I come up with a new value. Just divide that by 3,600,000. I would get 0.6 kilowatt hours. Okay, so from a consumer standpoint, that sounds much, much smaller and more agreeable in terms of our energy consciousness, or when I go to look at it costs 5 cents per kilowatt hour. So you can see 0.6 times 5 cents, you're looking at what, 3 cents to run this light bulb. Okay, so now case 2, and I want you to pick this up because this is a really easy way to do this problem. 25 watts. Okay, so 25 watts, if we wrote that as a kilowatt, so this would be 0.025 kilowatts. Okay, if I take these two pieces together, 4 hours a day, 6 days, that's 24 hours total. Okay, so if I find the energy here, and watch this, so 0.025 kilowatts times 24 hours. Notice the units. So if you take your 0.025 times it by 24, oh my goodness, you get 0.6 kilowatt hours. Okay, now if you know both, fantastic. One's obviously faster than the other, but you have to really understand what you're doing in blue to be able to go that route, but I'll leave it up to you. Okay, and then both would be 3 cents by the time you're done. I'll leave you with questions 1, 2, and 5 from section 5.5. Again, you're always welcome to read more in those sections. You'll probably find more interesting information. I left out a couple of sample problems, so this is some of the sample problems that are in your textbook, so you don't need me to go through them. You can look at those and reveal the answers, and there's 2 sets there, so there's another 4 or 5 questions you could try to practice. Okay, so just going back to here, section 5.5, 1, 2, and 5, if you could give those a try, please. And I'll point out that I already did this one for you, so that should not be a difficult question to solve. Thanks for tuning in.